Alright, my god, this paper is long, okay? So paper 4 is very long for a reason. So I haven't really checked any of my work, yes, but I've tried to be careful as much as I could. That's probably why I'm taking quite a long time, in addition to me thinking out loud and continuously talking. Anyway, so I hope this is nearing the end. If you spot any error in my work, so please let me know. I'm not perfect, and neither have I ever said that I'm perfect. Without checking the work, I could really be making mistakes here and there, and as I get tired, I lose concentration and mistakes will start to crop up. And it's the same thing when you sit for an exam. You are running a marathon when you do a 2-hour paper 4, so you gotta stay focused, you gotta take things one at a time and just be careful, but you gotta leave some time to actually check through the work and not having the luxury of going back and do the whole paper again. Question 9. So we have this compound CXHYOZ. Part of that mass spectrum is shown. This is mass over charge, just like the first question, which was on relative atomic mass. So everything in mass specs is to do with mass over charge. Everything you see is a charge species of +1 charge. This is relative intensity. So it's not really percentage. We have a peak height of m and m plus 1 of 33.9. So this is m. Actually it's m and then plus because it's cationic, because it's charge. And then this is m plus 1 plus because it's cationic again and again. Let's mention that. So how do you work out x, which is the number of carbon atoms? So the relative percentage or the relative intensity of the m and m plus 1 peak allows you to work out the number of carbon atoms in this formula stated in the syllabus, something you are supposed to know just factually. Alright, so that is going to be the percentage of m plus 1 divided by percentage of m. So x equal to 100 over 1.1 times the percentage of m plus 1 is 3.4. So it's 3.4 divided by 33.9. So pop that into your calculator. So 100 divided by 1.1 times 3.4 divided by 33.9. I got 9.118, and well, number of carbon atom has to be rounded up to the nearest whole number. So this is the nearest whole number. Not three significant figure, not like follow the data or whatever, because this is the number of carbon atom. It has got to be a whole number. For 2 marks, you must be doing something wrong if you're not scoring these 2 marks, presumably because you don't know the formula, and this is clearly stated in the syllabus. Candidate should be able to blah 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 blah. Next bit, so deduce the molecular formula of T. So the parent ion, so this is what you call the parent ion, is exactly 150. Okay, so the parent ion is exactly 150. The m over e or m over z is 150. I have 9 carbon atoms. Okay, so 9 carbon, so it's C9. H, I don't know what else, HY or Z, right? HY or Z. So 9 carbon atoms is going to be 150 minus 9 times 12, because there's the relative atomic mass for 1 carbon, and I have 9 carbon. So 150 minus 9 times 12, that's going to give me 42. So I must have oxygen and I must have hydrogen. So what if, so this is going to be split between oxygen and also hydrogen. Okay, well, I said oxygen and hydrogen, but I wrote down hydrogen and oxygen, doesn't matter. So if I have 1 oxygen, so if I have 1 oxygen, then 42 minus 16 times 1 is going to be, so all I'm doing here really is try and error, 26. So 26 hydrogen, 42 carbon and 26 hydrogen. What is likely and what is not likely? I should really use the other mass spectrum here as well for use instead of randomly guessing. So this is around, where is this, 100 to 5, so 105, 110, 115, so this must be 120, So if there is 120, this is probably 119. So 145 to 119. Oops. Oh my good old calculator. So there's a difference of 26, and I don't know why is that 26. Don't know. Okay. This is getting harder and harder and harder for me. So I was thinking like if I have that, then I'll have C9H26 or 1. But then when you have 9 carbon, you know how in alkanes, okay, so example for alkane, you have CnH2n plus 2, and there's the maximum, right? So 2 times 9 plus 2 is going to give you 20 hydrogen. And here you have 26 hydrogen, which means the oxygen must form a lot of bonds to the hydrogen, and that is when I can tell that is most likely wrong. There's too many hydrogen for the right number of carbon. I'm not saying it's alkane, but remember alkane, where everything is saturated, there's the maximum hydrogen you can get when it's saturated, right? And this is way more than the saturated hydrogen that you can have, because that would mean the oxygen form a lot of bonds, and that is unlikely. So if one oxygen is unlikely, how about then if I have 2 oxygen, then I'll have 42 minus 2 times 16. So 42 minus 16 times 2, I get 10. So that is 10 hydrogen. So C9H10O2. 10 is more likely because that is lesser than the maximum number of hydrogen, unlike the previous one. So I'm more than happy with C9H10O2. And for 1 mark, and suggest, I don't know, I mean, you probably can suggest from this diagram alone, but it's not the easiest thing to read in the world, you see. So it's like, it's interval of 5. I wasn't even sure if this is 119 or something. This could be 80, 85, 90, 91, 92, something like that. 91, 92. And then this is exactly that, so 50, 60, 65. Rather than spending a lot of time on this, I have resorted to this trial and error and thinking about things like this. I have spent more than 1 minute on this, and really I don't know how else to do this for 1 minute. And if you know there's another way, so let me know. I'm always interested to know, like what else can I do to make it simpler. All right, the fact that I say deduce usually means that you should be able to get it from the data, but I don't find it to be that easy. Okay, usually by right we should look at the fragmentation based on the difference in the mass over charge. It's just too much effort. Okay, but I mean, I think I've gotten what I needed from just working through the logic. Anyway, so part 3, the mass spectrum has a peak of 119, mass over charge ratio. Identify the fragment loss from T to produce this peak. So C9H10O2 is going to be, remember, everything in the mass spec is +1, so that is equal to the molecular ion peak that was at 150. So 150 minus 119 is 31. Oh no, my calculator is starting to show its age. Oh no. Anyway, one of my buttons has started to come out a little bit. So what has been lost? So this is the fragment that has been lost. We're looking at 31. We must have carbon, hydrogen, oxygen. For 31, it could be 2 carbon. So if it's 2 carbon, it's 31 minus 12 times 2, that's 7. And if it's just 2 carbon with hydrogen, that doesn't really make sense. How about if it's got 1 oxygen? Because oxygen is a lot heavier than these. Each oxygen is 16, so 31 minus 16, and I got 15. 15 is a very magical number because CH3 is going to be 15. So most likely CH3O, where you have lost 1 oxygen together with that CH3, therefore CH3O, and this is the fragment loss. So this is not what you see, this is what has been lost, and therefore you see whatever this one minus this one with a plus. Okay, So a lot of mass spec is just coming down to speculation based on the fragmentation pattern. Next one is this infrared spectrum. So for infrared, we look for two things. Are there any broad spectrum? Are there any broad absorption, around these 3300 or 3200 cm minus 1? There is nothing there. So no OH. The other one is around this region. Is there a sharp absorption? Of course there is one. So there is a C double bond O. Okay. So for V, very clearly there's a C double bond O because they want the type of bond. You wouldn't be able to tell functional group ever from infrared straight away. But if you have the structure, you can refer to the data booklet and they can tell you based on the functional group roughly where you will find the absorption, but then you still need the actual spectra to correspond it to and to check. Okay. W is way lower than 1500, but judging by how we know the infrared spectrum of T, it's got an oxygen. A CH3O is going to look like this, like that, right? Okay, so the fact that you have that, and if you look in the data booklet under infrared, so something that has oxygen, well, the first row is a alcohol, ethers or esters is a strong absorption between 1040 to 1300. So this is 1300, this is 1200 cm minus 1, so these are wave number. So this is in the right region for C single bond O of alcohols, ethers and esters, and it's a pretty strong absorption as well, and I got this consistent with what we have discovered from the previous part of the question. Alright, so a lot of these they relate to each other. Okay, proton NMR. So earlier in the question there was something on carbon 13 NMR, but now it's proton NMR, and the first thing I can tell you, somewhere around this region between 7 to 8, that is what we call aromatic proton. Okay, so something to do with benzene ring. When you have a proton on a benzene ring, they will appear in the aromatic 7 to 8, and these are the first thing we know appear when we are in research lab. When we have a lot of phenyl groups, we will have a lot of signals around here. That's because that's where the aromatic protons belong to. Okay, so the type of proton, if you look carefully under the proton NMR categorization, do they call it aromatic protons? They call it CH attached to aromatic ring. So when you have a CH attached to aromatic ring, that is called an aromatic proton. Okay, and in the case of this 3.9, so we're looking at these, 3.9 is pretty high, and 3.9 we're probably looking for alkyl next to electronegative element, because this looks more like CH3O. So it looks like when you have this bit as shown here, as well as consistent with the mass spec in the previous part of the question. So these three hydrogen, they are next to an electronegative atom. So this is a CH alkyl. Oh, no. CH alkyl next to electronegative atom. In this case, it's probably oxygen. Pretty stingy to give just 1 mark, alright? Anyway, so the peak at chemical shift 2.4 parts per million is due to a proton attached to a saturated carbon atom. A saturated carbon atom means a carbon with 4 covalent bonds. Is it? No, that is not right. That is not right, because a carbon with 4 covalent bonds could also mean you have carbon-carbon double bond. That is not right at all. Only carbon-carbon single bond. Okay, so 2.4 ppm. Let's have a look at this 2.4 ppm. So it's also a singlet, and it's got, so it's a CH3, so it must be bonded to something. And it's bonded to a carbon because this one is bonded to oxygen. It's got to be CH3 because there's 3 hydrogen as part of the integrated ratio. It tells you how many, how do I say this? I don't like this at all. What am I talking about? It's due to a proton attached to a saturated carbon atom. It's attached to a saturated carbon atom. So it's a CH3 bonded to something. It's a CH3 bonded to something attached to a saturated carbon atom. Saturated carbon atom. Well, this carbon is saturated. Alright, this carbon is definitely saturated. It's a single bond. So these protons are attached to a carbon which is saturated. I've got oxygen and I've got a carbonyl. So I've got a carbonyl. So if I look in my data booklet, the thing that has carbonyl, I could have a alkyl next to a carbonyl. If it's just carbon like this, it would give me splitting. But this is a singlet, so there's no neighboring protons. So perhaps with no neighboring protons, because it was a singlet, if you see here, it's a singlet, no splitting at all. CH3 with a singlet will refer to a CH3CO, or you have a aromatic ring, you have a benzene ring, so the CH3 could be next to a something like this. Alright, so it could be next to a benzene ring because there's no neighboring proton here. Let me check the data booklet. So an alkyl, a CH3 next to a carbonyl is around 2.2 to 3.0. So this thing here is 2.2 to 3.0 ppm as stated in the data booklet. And then I will have CH3 next to an aromatic ring. So this is not aromatic proton, this is an alkyl next to aromatic ring. Again, is 2.3 to 3.0 ppm, and that is consistent with this because there are 2 possible type of protons. They will give you a singlet with no neighboring protons at all, therefore giving you a singlet. The 2 possible type of protons, so you have a CH alkyl next to C double bond O, or it could be CH alkyl next to aromatic ring. So the first 2 rows in the Proton Nmr chemical shift in the data booklet. So now we're going to add a bit of D2O. D2O is what you call deuterated water. So it's got deuterium isotope, and it said does not change its Proton Nmr spectrum. When the Proton Nmr spectrum loses a resonance or 2 chemical shift or 3 or whatever, when it loses any chemical shift in the presence of deuterium, D2O, deuterated water, they will tell you there's labile protons. But if it does not do that at all, so no labile protons, i.e. no OH or NH. So both OH and NH are what you call labile protons, not just OH, yeah, okay, in T. Because this is a negative result, so there's no such group in the molecule. Whereas if it is a positive result, then you have labile protons. You must have either OH or NH in the T. However, you can probably cross out NH. Why? Because T is, remember earlier in the question, what was T? T is C9H10O2. So C9H10O2, no nitrogen. So there's no point of me thinking about NH. So no OH applies in the context of T because of the particular molecular formula discovered earlier in the question. Okay, the end of the question now. Now, 2 possible structures which are functional group isomers. So functional group isomer comes under structural isomers. So molecules with same molecular formula but different structural formula. So what can we say about it? So there is no OH. So 2 possible structure, yeah, okay. There's no OH. And we could have a CH3 next to CO, or CH3 to a benzene ring. Okay, so if I draw to the benzene ring first, I have a CH3 there. I have 4 carbon in the ring. I have a CH3 next to the benzene ring. I have 4 hydrogen in the benzene ring, and then I have a CH3O. Okay, so CH3 next to a single bond O. So what could I do? I could get O CH3. So this will give me 6 carbon, 7 and 8 carbon. That is not right. Is that right? That is not right at all, because I'm looking for C9H10O2. C9H10O2. I don't want to add oxygen here because this is already fixated by what is the possibility, and I have no OH, and I have 1 extra carbon. So here there's only 6, 7 and 8. I have 1 extra carbon. So if I have 1 extra carbon, so it could be a CH2. What was it just now? Or CH3. So 6 carbon, 7, 8, 9. The hydrogen will be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 is also wrong because here I'll have 2 extra hydrogen, and I only have 3, 3 and 4. I have a 3, 3 and 4, but I have 2 extra hydrogen. No, 2 oxygen. I only have 1 oxygen, so I could have an ester. This is an ester, just C double bond OO. This could be one of the isomer. And if this is the isomer, what is the other one? The other one will also be a benzene ring with 4 hydrogen, so it must have 2 substitution. All I've done is I've shown the 1-4 substitution, 1 and 4, but you could you could also potentially have the isomers at any of these positions, as long as they are at different position, as long as you continue to have 4 different protons, sorry, not 4 different protons, as long as you have 4 protons on the benzene ring, that will have been okay, as long as the double substituted benzene ring. What else could I have? I could have a CH next to a C double bond O, like this. So I could potentially have that, a CH3 C double bond O. So that is perfectly acceptable. What else then? Could I have all CH3 then? 6, 7, 8, 9. This is a CH3 next to a CO. This is different from this. And then I have 3 hydrogen, 3 hydrogen, and 4 hydrogen. And this one would appear just like this here. This one would appear here, and the 4 aromatic protons will appear there. So this and these are different because this is this is a ketone and this is an ester. Alright, so it's a suggest question, so I wouldn't be worried that if you can come up with a different answer. As I said, the position of the substitution shouldn't matter that much. You could have the ketone here or here, as long as you have 4 aromatic protons consistent with whatever has been shown in the NMR spectrum. Okay, and these are the CH3 next to CO. These are the CH3 next to an aromatic ring as the 2 possible types of protons for this particular signal. Alright, and there's no OH, so I did not do any OH at all. So you cannot do a carboxylic acid, even though you know that esters and carboxylic acids are functional group isomers, but you cannot do carboxylic acid because no left out protons. If you have carboxylic acid, you have OH, but these are negative results, so there's no OH. You cannot draw carboxylic acid there. I have shown the CH3 in this formula here because this was my sketches to see whether it's right or not, and this is the proper skeletal formula I've drawn for the final structures. They have set 2 possible structures. They did not specify display or skeletal or structural. If you watch my other created playlists on organic chemistry, you will know that I like to use skeletal. It's fast, it's elegant, it's easy to check. Okay.